In this video, we're going to learn how to calculate the acceleration in spherical coordinates. Just like in any other coordinate system, the acceleration is the second time derivative of the position vector. And just as a disclaimer, in this video I'm going to use the dot notation to keep things shorter. So, for example, x dot would mean the same as the time derivative of x. That spherical position vector we need to differentiate is this one right here. And since the vector in those brackets is simply the radial unit vector in spherical coordinates, we can simplify this position vector as r times er. So that's what we're going to have to work with. In order to differentiate this thing 2 times with respect to time, we need 3 essential concepts. We need the product rule for differentiation, because a lot of the stuff we're going to be working with is clumped together via multiplication. Then we need the chain rule for differentiation, because the angles are time dependent as well in spherical coordinates. So if we have, for example, sine theta, the time derivative of that is not just cosine theta, but cosine theta times theta dot. Since theta and phi and r are time dependent, we need the inner derivative as well. So that's why we need the chain rule. And thirdly, we need the time derivatives of the unit vectors in spherical coordinates. Usually, if you have a problem that's asking you to calculate the acceleration in spherical coordinates, those will be given on a formula sheet or underneath the problem or whatever. But in case you have to differentiate those yourself, I made a video about that as well and linked it in the description below. So in case you need it, you can watch that one first. Now, with that out of the way, let's get going. As we saw before, our starting point is the position vector, and in spherical coordinates that position vector is r times the radial unit vector. Since this is a product and both are time dependent, we need the product rule. First, we're going to differentiate the r and leave the unit vector as a constant, and then we're going to leave the r as it is and differentiate the unit vector with respect to time. So that one gets a dot. And now you see why we need the derivatives of the unit vectors as well, because now, since we have er dot right here, we can instantly plug that one in. So we get r dot times er plus r times, and now we're going to plug in this one right here. So we end up with r times theta dot e theta plus sine theta e phi dot. We can simplify this further by distributing this r into the bracket. So we get r dot times er plus r theta dot e theta plus r sine theta e phi dot. So this is our first time derivative, but since we're looking for the acceleration, we need to differentiate it a second time. And for the sake of readability, I'm going to color code this, because this is going to be long. We have a normal product rule here, we have a triple product rule here, and we have a quadruple product rule with a chain rule here. So let's get started with the blue term. We have r dot times er. Using the product rule on that, we're first going to differentiate the r dot, which is going to give us r double dot, and leave the er as it is, plus, now we're leaving the r dot as it is, and differentiating er with respect to time. And since we have er dot here again, we can simply plug in this derivative. Now onto the red part. So we're going to start by differentiating the r with respect to time, which turns it into r dot, and the rest simply stays as it is. Then we're going to differentiate the theta dot, which turns it into theta double dot, and leave the rest as it is. And lastly, we get r theta dot times the derivative of this unit vector, so e theta dot, which is this one right here. So we're going to plug it in. That is the red part done. Now we're going to take care of the green part, which is a quadruple product rule. Just like before, we're going to go from left to right. So for the first part of our quadruple product rule, we're going to differentiate the r and leave the rest as a constant. So we get r dot sine theta e phi phi dot. Now we're going to differentiate the sine theta and leave the rest. So we get r times, and now the chain rule comes into play because the derivative of this sine theta is cosine theta times theta dot, since we need to take care of the inner derivative as well. So we get cosine theta, theta dot, times e phi times phi dot, plus, now we're going to differentiate the unit vector and leave the rest. So we get r sine theta, and then the derivative of this unit vector is this right here. So we're going to plug that in right away. And then lastly, we're going to differentiate the phi dot and leave the rest standing, which gives us r sine theta e phi times phi double dot. Now, technically, this is the result. This is the acceleration in spherical coordinates. In order to make this a little bit easier to work with, we can now distribute the brackets, and afterwards we can dissect this into its components. So the radial component, the theta component, and the phi component. We're going to do this line by line. This one is pretty much already simplified. We can just copy that, r double dot times er. For this expression here, we're going to distribute the bracket, which gives us r dot theta dot e theta plus r dot sine theta e phi phi dot. This one and this one don't require any attention. We can just copy those. R dot e theta plus r theta double dot e theta. For this term right here, we can distribute the bracket again. And since we have this negative sign right here, we're going to get minus r theta dot squared er plus r theta dot cosine theta e phi phi dot. For those two, there is nothing to distribute, so we can just copy them again. Here, we're going to distribute the bracket, which gives us, since we have negative signs here and here, we get minus r sine squared theta phi dot squared er minus r sine theta cosine theta phi dot squared e theta. And lastly, this one right here, plus r sine theta e phi phi double dot. So this thing right here, it looks horrible, but this is in fact the result for the acceleration in spherical coordinates. What we can now do is dissect this thing into its components. So we get a radial component, a theta component, and a phi component. Now, the way you would usually do this in Cartesian coordinates is if you have a unit vector, let's say ex in Cartesian x direction, and a scalar is multiplied to that vector, let's say 3 times ex. This thing, the resulting vector, still points in x direction, because this scalar does nothing about the direction. And that's what we're going to use here. In order to find the specific components, we can simply sort this result by its unit vectors. For example, this one has e theta as its unit vector, so it points into theta direction and thus contributes to the theta component. So first, let's look for everything that has a radial unit vector. This part right here, this expression, and this one. So if we now collect the scalar factors, for the radial component we get r double dot from here minus r theta dot squared from here minus r sine squared theta phi dot squared from here. Doing the same for the theta components, we find that this term, this term, this term, and this one have theta unit vectors. So collecting those, for the theta component, we get r dot theta dot plus r dot theta dot plus r theta double dot minus r sine theta cosine theta phi dot squared. Since those two are the same, we can simplify it by saying 2 r dot theta dot plus r theta double dot minus r sine theta cosine theta phi dot squared. And lastly, for the phi component, we find that all of these other terms contain phi unit vectors, and collecting their scalar factors, we get r dot sine theta phi dot plus r theta dot cosine theta phi dot plus r dot sine theta phi dot plus r cosine theta theta dot phi dot plus r sine theta phi double dot. And since we have this one twice and this one twice, we can simplify again, which gives us 2 r dot sine theta phi dot plus 2r theta dot cosine theta phi dot plus r sine theta phi double dot. So now we have not only calculated the acceleration in spherical coordinates, but we have also dissected it into its individual components. Thank you so much for watching, and see you in the next one.